one time I flying 3 times. So,
Okay, so today's tutorial, we're still on the subject of memory hierarchies and looking at cache performance. So,
what are the number of misses when using no right allocate and right allocate? I can't remember.
the first question is talking about right miss policies. So, in the question, it discusses two right miss policies. The first policy is that when you're writing to a location, then you write the value into the main memory only, and you don't bother bringing that value into the cache. Okay, so that's called no write allocate. So when you write, you just write to the main memory, and you don't bring it into the cache. The other policy is the write allocate policy, which when you write to a location, you allocate a cache line or cache block for that data, and then once you've allocated the cache block for the data, you write the value to the cache rather than to the main memory. Okay, so we have these two different policies, and we're given a sequence of write to reads. We have 5 memory operations. First of all, we write to location 10, and then we write to 10 again, then we read from 20, write to 20, and read from 10. And we're asked to analyse behaviour under these two policies, under the no write allocate policy and under the write allocate policy. And we're asked to calculate the number of hits and misses. So what if we have a no write allocate policy? First of all, we write to location 10. Will that be a hit or a miss? We assume that the cache is initially empty, and we want to write to location 10. Hit or a miss? It's going to be a miss because the cache is empty. There's nothing in the cache. So the first write will be a miss. What about, then we write to location 10 again. Will that be a hit or a miss? Okay, for the no write allocate policy, it's going to be a miss again, because remember that when we're just writing to a location, we don't allocate a cache line. So although the first 10 is a miss, because it's a no write allocate, we don't allocate a cache line, so the second write to a 10 will also be a miss. We then read from 20, hit or a miss? Miss. The read from 20 will be a miss. Then we write to 20, hit or a miss? Hit. This is going to be a hit, because here we're reading a location. So when we read the location, even though we have a no write allocate policy, when we're reading the location, we will allocate a cache line for that memory. Okay, so this read 20 will allocate a cache line, and then when we write to 20, we have it already in the cache, so that will be a hit. And then the last write to 10, hit or a miss? That will still be a miss, because we've only ever written to location 10, so we've never allocated a cache line for it. Okay, now we want to do the same thing for the write allocate policy. So the first write to 10 will again be a miss, because we start off with the cache empty. What about the second write to 10? Now in this case it will be a hit, because with the write allocate policy, the first write to location 10 will have allocated a cache line for this location. So when we write to 10 again, we have a hit. The read from 20 will be a miss as before, because we haven't allocated 20 yet. The write to 20 will be a hit as before. What about the last write to 10? That now will be hit. Okay? So in the first case we have 1 hit and 4 misses. In the second case we have 3 hits and 2 misses. Okay, so that's question number 1. Any questions on question number 1? Okay, so question number 2, we're given 2 tables. The first table is a table of cache misses in terms of percentages. And this is given for different block sizes or different cache line sizes and also different cache sizes. So this is the total cache size and this is the block size. So those are the miss rates for these different values of block size and cache size. And then we're also given a second table which is the mean access time. Okay? And we're asked to fill in some missing entries. So we were asked to calculate this value x here, which is the percentage miss rate for 64 block size and cache size 64K. And we're also asked to calculate y and z. Again, block size 64, cache size 16K and 256K. Okay, so how do we do this? First of all, we're given some more information. We're told that the hit time is 1 clock cycle. Okay, so if we have a hit, it just takes 1 clock cycle. If we have a miss, we have a miss penalty. And the miss penalty will depend upon the size of the block we're trying to bring into the cache. Okay, so we're told that there's an 80 cycle penalty to begin with, and then for every 16 bytes we want to load into the cache. That's going to take 2 extra clock cycles. Okay, so if we have a 16 byte block, it will take 82. A 32 byte block will take 84, and so on. So, if you remember from last week, we have a formula. Okay, the formula we had last week was that the mean access time is equal to the hit rate plus the miss rate times the miss penalty. So we want to calculate this value x in the table. X is the miss rate we want to calculate. We know the hit rate is 1, and we're asked to calculate x, and x is for a 64 byte block. So for a 64 byte block, what will the miss penalty be? It'd be 64 bytes, what would the miss penalty be? 88. Okay, because it's 2 cycles for every 16 bytes, and we have 64 bytes. Okay, so we have a miss penalty for 64 bytes is 88. So we can put our x into the formula. So the mean access time is going to be 1 plus x times 88. And we know the mean access time from the other table. If you look at the other table corresponding to the position of x, then we have a mean access time of 1.93. Okay, so the 1.93 comes from the second table. We want to find the value of x in the first table, so it's just a simple calculation. X is 0.93 divided by 88, or 1.06%. Okay? And then we want to calculate the missing entry y in table 2. So y is a mean access time. So again, we could use the same formula, except that this time we're calculating the access time from the missed rate. So again, if you look at the first table, you can calculate, you can obtain the miss rate, 2.64 from the first table. We multiply 2.64 times 88, the miss penalty, because it's a 64 byte block, and we get a mean access time of 3.32. So can anybody do the last one for me? The value of z in the second table, again, it's a mean access time for block size 64. Can somebody calculate what z should be? It's the same formula, yes? 1.45, okay. Okay, so it's the same formula. If you look at table 1, we have a miss rate of 0.51. We multiply 0.51 by 88. 0.51% by 88 and add 1. Okay, any questions on that so far?
How you get 88 again?
88 again. For the miss penalty to go to memory is 80. Then in the question, every 16 bytes, right, is 2 clock cycles. So
Okay.
64 divided by 16 is
So this is our new table that we have. We filled in the value of x, y, and
64
z.
divided by 16 is 4. So it's
And we've
Four
asked
times
some
8, right?
more questions
80
about
plus 8, 88.
this new table now.
He just said that.
Okay, so which block size has the smallest average memory access time? And we've asked to give the answer for 16K, 64K, and 256K. Okay, so the other screens show the updated tables. We want to look at table 2. For 16K, the 16K cache size,
1.4.
which block size gives the minimum access time?
256K.
64, okay. If you look at the table, cache size 16K, 64 has a mean access time of 3.32, which is the smallest.
Yep.
What about
For the smallest number.
what about a 64K cache size? Which block size is the smallest? 64 again. And what about 256K cache size? Okay, again 64. So 64 byte block gives the smallest mean access time for cache size 16K, 64K,
Sure.
256K. What about the minimum risk rate?
Still got. Sorry.
So for a cache of size 16K, which has the minimum miss rate? 64 again. What about 64K cache size? 64K cache size? 128. And 256 cache size? 128 or 256, yes. So, are these the same? Does the block size that give you the minimum miss rate also give you the minimum mean access time? No. Okay? So, can anybody tell me why not? Why aren't they the same? Because you would expect if you have a smaller miss rate, you should have a smaller mean access time. Why aren't they the same? Sorry? Yeah. Okay. So the reason is that the penalty, the miss penalty, depends upon the block size. Okay. So for a larger size block, you have a larger miss penalty. So although the miss rate, although the minimum miss rate for 64K is a 128 byte block, a 128 byte block will have a larger miss penalty than a 64 byte block. So although it has a smaller miss rate, the smallest mean access time is actually 64 byte block. Okay? So in general, a smaller miss rate will give you a smaller access time, but it doesn't always hold because there are other factors you also have to consider. Any questions so far?
The bigger the block size, the higher the miss rate.
Okay, so let's move on. Again, a question about these tables. So if you look at the table 1, you will see that as you increase the block size, then the miss rate first of all decreases, but then as you increase the block size, the miss rate starts to increase. So can anybody give me a possible explanation for this? Why might this happen? Sorry?
Bigger block size, higher.
So increasing the block size, so that explains why increasing the block size can cause an increase. Sorry? Decrease the block numbers, yes. Okay. So but how do you explain the fact that first of all it decreases? Okay, so here's a possible explanation.
Is the ratio of the block size to your cache size?
It will depend upon your particular program, but if your program has good spatial locality, which means that when you're accessing the data, you access data that's close to one another. If you have good spatial locality, then as you increase the block size, you're going to be able to take advantage of that spatial locality, and increasing the block size can then reduce the miss rate. increasing the block size can also have some negative effects. As we've just mentioned, first of all, increasing the block size will increase the miss penalty because it's going to take longer to load a larger block into the cache. If you have a larger block size, but your cache size is the same, so having a larger block size but the same cache size will mean that you have fewer cache blocks, called cache frames. So that can cause conflicts because if your program wants to access a location that's not already in the cache, it will have to replace when the cache is full, or when a set is full, it will have to replace a cache block. So that can cause conflicts. And if the cache is small, increasing the block size will mean that there are fewer blocks overall. So again, that can also cause misses. Okay, so increasing the block size can reduce the miss rate under certain circumstances when you have good spatial locality, but there are also these negative effects as well.
Yeah, technical term for conflicts among skills.
Sorry?
Conflicts among skills. Yeah, technical term. And what is the case?
Okay. So it depends upon what sort of cache mapping you're using. Last week we talked about a direct mapped cache and an n-way associative cache and a fully associative cache. So what we mean by a peer is a cache is a location that shares so the peers are the blocks that share the same cache frame. Okay, so if it's a direct mapped cache, then the peers for a particular cache frame are those blocks which are mapped to that cache frame. If it's an n-way associative cache, then the peer blocks are the blocks which can share the same set. Okay? If it's a fully associative, then the peers are all everything. And then we noted that the block size that gave the minimum miss rate is not the same as the block size that gave the minimum access time. So which is most important, the miss rate or the access time? Yeah. In the end, when it comes down to the efficiency of execution, it's the access time that's important. Okay, so although you want to reduce the miss rate, the main emphasis should be on minimizing the access time. Okay, any questions on question number 2? So let's go on to question number 3. So here we're told that we have a byte addressable machine and we have a very small cache. The cache can only hold 8 32-bit words, and we're told that each cache block consists of 2 32-bit words. Okay, so we only have 4 blocks in our cache. We're told that the cache is initially empty, and then we're told that the program reads data from the following sequence of hex addresses, 2F4, 208, 200, etc. And we want to know, or we want to show the contents of the cache and compute the hit rate. Okay, so first of all, we're going to do it for a 12-bit. First of all, we're going to do it for a direct mapped cache. We have a 12-bit address because our addresses are 3 hex digits. Okay, so 3 hex digits will give you 12 bits. So we have a 12-bit address. If we have a direct mapped cache, then remember, for a direct mapped cache, each block is mapped onto a particular cache frame. We have 4 cache frames, or 4 cache blocks, because from the question we're told the cache size is 8 words, and each cache block or frame is 2 words. Okay, so we have 4 cache blocks, so we need 2 bits to index to a particular cache frame. And then within a block we have 2 words or 8 bytes, so we have 3 bits to index to the 8 bytes in a block. Okay, so let's see what happens when we execute our program. Okay, so first of all we access to F4. So with a direct mapped cache, then the bottom three bits of the address are the byte within the block. The next 2 bits of the address will give you the index to the cache frame, and then the upper bits of the address will give you a tag which identifies the different pairs for that particular cache frame. Okay, so in this case the tag consists of 7 bits. The top 7 bits are the tag, the next 2 bits are the index, and the bottom 3 bits are the byte address within the block. Okay, so first of all you have to identify the 2 bits which will index into the cache frame. That's going to depend upon the size of the block. Okay, but in this case a block is 8 bytes. Everybody happy with that? Do you understand? Okay, so using the direct mapped approach, 2F4 will be mapped onto cache frame 10, but the cache is initially empty, so that will be a cache miss. The next address is 208, so 208 will be mapped onto cache frame 1. Again, that will be a miss because the cache was initially empty. 200 hex mapped onto cache frame 0. Again, a miss. 2F0 this will be mapped onto cache frame 10, and if you look at the tag, 2F0 and 2F4 are actually within the same block. Okay, it's a different location, a different address in memory, but those addresses are next to each other and they are mapped onto the same block. And 2F0, that block is already in the cache, So 2F0 will be a hit. Okay? Two 0C mapped onto cache frame 1. Again, if we look at cache frame 1, we already have a block in cache frame 1, and in fact it's the same block that we want.
There's no table.
So 20C and 208, again, next to each other, they are mapped onto the same, they're within the same block, and that block is already in the cache. So we have a hit for 20C. 304, if you look at the index bits, it should be mapped onto cache frame 0. We already have something in cache frame 0, so we have to replace 200 hex. We have to replace this cache block by this cache block. Okay, these two blocks are mapped onto the same frame. This will be a miss, and we will have to replace 200. And then after that, we access 200 again, but we've just thrown this block out of the cache, so therefore it will again be a cache miss, and we have to replace the previous block that we just put in. And then we access 204. Again, this is in the same block as the one we've just loaded, so that will be a hit. So we have 3 hits out of 8. Okay, any questions on that?
Why is it a miss?
Wait. Which one? 2O? Wait, let me see. 2F0, right? 0010, 111, index 1010, 000, it's a hit.
Okay.
Then 1305 is a hit.
Sorry?
Why do you say that it's a hit? Because same index is a hit.
Same tag, same index, right?
Okay, so
Oh, yeah.
we're now told
This one also,
to
right?
consider a two-way
And this one is
set
not.
associative
Or
cache,
different.
Yeah. But I think
and
that's
we're
the
going
last
to
one.
have the
the
least
last one?
recently used, or LRU, policy for replacing caches. So with the 12-bit address, then again we have 3 bits for the byte address, okay, because we have 8 bytes in a block, so we need 3 bits to index to the bytes within the block.
Why is this a miss?
With a two-way associative cache,
Because
we only have 4 cache frames altogether, and it's two-way associative. So that means we'll have 2 sets of 2 frames, okay? Because we only have 4 frames altogether. So now our index has to index between the different sets. We only have 2. I think this is the least recently used. In fact, the block is the same as this block, and this block was used quite recently. So in fact, we have to replace 200X. And then when we access 200X, we get a miss. In this case, the least recently used in set 0 is 2F0, so we have to replace that one. And then for 204, we have a hit because it's the same block as 200. Okay, any questions on that? So, if you're given a question like this, first of all, you have to be careful in working out how the address is used. Okay, so how the address is used will depend upon your block size, how many bytes of block you have,
Yeah.
and it will depend upon how many cache frames you have. So if it's n-way set associative,
Look at
you have to work out how many frames you have altogether, how many frames you have in each set, and then you can work out how many bits you need for the index. And then the top part of the address will be the tag that distinguishes between the P and box.
So this 00 and this 00, the tag different.
Okay?
So if you
No
want
questions?
this, right, you need to remove
So
this.
let's go on.
Because the element, you need to remove this. So put this in.
Okay.
Then the next one, 0, 0, 1, 0, 0, 0, 0, 0, 0 again. And because
Meaning
now
for the
this
direct
one is inside, not the previous one. This one is
Okay,
inside.
so question
you
4
then
and
mix
5
it.
are
So
more
you
general
remove this
questions.
and put this in.
Oh, it's
We mentioned that
When the tag and the index is
the overall objective really
They don't count
is
that.
to
yeah.
minimize the
This is
mean
inside
access
it, right?
time.
Then 0, 0, 1, 0.
Okay, because that is what
is inside. It's a heap.
ultimately affects the execution of your program. So we're asked
Tell you what,
to
it's only-
name
only the
some optimization
and the index is the
techniques
same.
which can be used
they
to
get that?
improve the
they
performance
get
of
that
cache
value?
memory.
The 3-bit
And-
hexel, right? All convert to binary.
Then how you know the
In
tag is
particular,
separate?
we're asked to identify
Format of direct method.
how each of these optimization techniques will
Tomorrow.
will
It's a
benefit.
format.
Okay, so we have some different types of misses. Okay, we have what are called capacity misses. So capacity misses are misses because your overall cache size is not large enough. Okay, so you can't put everything into the cache. If the cache size is too small, you will get cache capacity misses. We also have a term called compulsory misses. So compulsory misses refers to the misses that occur when you first reference a location in memory. Okay, so if the cache is initially empty and you reference a location in memory for the first time, then that will cause a miss, which we call a compulsory miss. Okay? And then we can also talk about conflict misses. So conflict misses are misses which are caused by the cache replacement. Okay, so you're accessing a memory location. That location may previously have been in the cache, but because we had a conflict, we replaced that cache block by some other block. Okay, so we call these conflict misses.
Put it in, right? It's quite
Okay, if you want to read more about this, you can look at Hennessey's book.
is the miss that occur due to
So let's
conflict.
discuss some basic optimization techniques. Okay. So first of all, you can have a larger cache, and that will help to reduce the capacity misses, and also having a larger cache means you can have more cache frames in general, so therefore that will help to reduce the conflict misses. We can have a larger cache block, and we've already discussed this in an earlier question. A larger cache block can help to reduce the compulsory misses due to spatial locality. Okay, so remember the compulsory miss is the miss that occurs when you access a location for the first time. If you have spatial locality in your program and you have a larger cache block, then even though you haven't accessed that location before, it may be in the cache memory, because it's part of some other block that you've accessed.
Larger.
But as we saw in the earlier question, having a larger block is not always a good thing, because if the cache size is the same, but you have larger cache blocks, then you're going to have fewer blocks in the cache. So a larger cache block could actually increase the capacity misses or the conflict misses if the cache size is the same. We can have higher cache associativity. What this means is by having an n-way set associative cache, but having a larger number of frames in each set, so that gives you more choice as to which cache frame you can use. Or if you have a fully associative cache, then you can load a block into any cache frame. So that can help to reduce the conflict misses. And some other optimizations, a multi-level cache can be useful. That will reduce the penalty for loading data, because instead of having to go to the main memory for the data, you can get the data from some other cache in the hierarchy. And another optimization which can improve performance is that given priority to read misses over write misses, again, this would depend upon the particular program, but in general, the reads are more important than the writes, and that can help to reduce the misses. Okay, so that's just a summary. As I say, you should read the book by Hennessy and Any questions? Okay, so okay, let's go on to question number 4 then. So question number 5. Question number 5 asks you to describe 2 approaches for quantifying the limit of instruction level parallelism. And what are the limitations in these approaches? Again, I'm not going to go into the details in the answer. You're asked to look at Hennessy's book again, and also there's a paper which describes instruction level parallelism by David Ward. So that's an interesting paper to read.
Reading easier than writing.
So let me briefly summarize the approaches. We're trying to get some upper bound on the amount of instruction level parallelism we can have. So one possible approach is to assume an ideal scenario. So in an ideal scenario, you can assume that you can have infinite register renaming, and you can have perfect branch prediction, and sort of perfect cache behavior, and so on. This can sometimes be useful in that it gives you an upper bound on the amount of instruction level parallelism you can get, but the limitation of this approach is that these assumptions are not realistic, and no real computer can achieve that.
What's
A second approach might be to assume a more realistic scenario. So rather than having infinite register renaming, you might put some limit on the amount of renaming you can do. Instead of assuming perfect branch prediction, you might have an actual predictor. I think in the lectures you've looked at different prediction mechanisms. You could have a kernel predictor, and instead of assuming a perfect cache, you might assume a particular cache design. So the advantage of this approach is that the assumptions are more realistic, but the limitation is that this is still an idealized model, and it may not correspond to the architecture of the computer that you actually want to know about. Okay, because this is just one model, and what applies to this model may not apply to the computer you actually want to use.
I got.
Oh,
Okay, so those are two possible approaches.
Just
0, 0, 1, 0 is 2, 1, 1, 1, 1 is F, 0, 1, 0, 0 is 4.
Another approach is to use modeling and simulation. So you
This
can actually benchmark your programs
I saw a photo.
So we just convert the
Three of
Different formatting.
to evaluate
They
how
don't
well
but address take only 3 bit. This one.
and you can have
Is this stated in the question?
computer modeling and simulation, which can be used to vary the settings of the parameters and
What
work
means
out
is in the notes.
how that
I mean the format.
how that affects it.
The format stated in the question.
But it's stated in the lecture also.
You say, I never really
If not, how you know?
Okay,
Must
so
be, must be, must be.
as I
It's the
say,
format, I
please
think.
read up about these topics. This is just a
Wait,
summary.
wait, let me read.
You can
But
find
you say
out
got
more
32
books.
bit words.
Okay, so I think we're running out of time. We have to stop there. Any questions?